All right, so hi, welcome back. It's a great pleasure to introduce Professor Ivan Losev, visiting from Yale, and he'll speak on an introduction to finite W-algebras.
Hi. So I was asked to speak about the work of my mathematical youth. I'm already in the age where it's pleasant, to talk about good old days. I'm glad you accepted this invitation. Let me start by introducing some notation. The base field for this talk is the complex numbers. G is going to be semi-simple algebraic group. Small g is the new algebra. Capital G. I'm going to identify with its dual as a Killing form. Which is for the purpose of being lazy and transfer some work from the speaker to the audience. Inside of G, I want to consider a nilpotent orbit. So here G is classical, is just an adjoint orbit of nilpotent matrices. I'm going to pick an element that I'm going to call E, and I'm going to include it into an SL2 triple. H and F, such a thing always exists by the Jacobson-Morozov theorem. And it's not quite unique, but it's unique up to the action of the centralizer P inside of G. This is the result of Kostant. Now, what are our goals for this lecture? First, I want to construct a transverse slice S inside of G, transverse to O, going to be an affine space, affine subspace of G. Second of all, I want to keep the algebra of functions on this S with a Poisson bracket. Once I have a Poisson algebra, it makes sense to quantize it. I'll explain what I mean by this later. And this quantization is a so-called finite double. So what I'm going to do, I'm first going to define this thing and explain its basic property. And then there are two constructions for 2 and 3. One via Hamiltonian reduction, and another is what I call slice construction. So I'm going to explain this in the second and the third part. And then if I have time, which I won't, I'm going to maybe tell you something about next steps in this study. So, who is this guy called S? So S is going to be the affine subspace form of elements of the form E plus something which commutes with F. So this is the centralizer. You can also say that it's carbon. That's a manifestly affine subspace in G. And why is it transverse? Well, Well, what do we need to check? We need to check that the tangent space at the point E, G, which is of course the same as G, is a direct sum of the tangent space to O and the tangent space to S. What is tangent space to O? This is provided as the image of adjoint of E. And by the very definition, the tangent space to S is a kernel of adjoint of F. Well, then this equality is a classical fact from representation theory of SL2. So this first part is just the representation theory of SL2, nothing else. So now there is one important construction which has to do with this S. Namely, there is a contract in this direction. I'm going to explain this. So we have this SL2 triple EHF, and it gives rise to a homomorphism from the group SL2 to G. Now I have a homomorphism from the one-dimensional torus across to SL2, and what it does, it takes an element T, and just sends it to the diagonal matrix, fitting inside of SL2. I can compose it to, I get a homomorphism which I'm going to denote by gamma. Now let me give you an exercise. So let's consider the following action of C cross on G, which we will call the modified action. Which is given by the following: the element T acts on an element X of my Lie algebra by T to minus 2 adjoint gamma of T times X. So then it has the following actions, the following properties. So first of all, T applied to E is equal to E. Second of all, S is C star stable. And finally, and perhaps most importantly, the action contracts for every element of S to E. Let me give it a number, 1. So it claims that the limit as T goes to infinity, T applied to S is equal to E for every S in S. Okay, that's why this action is called contract. And then property can be reformulated algebraically. Namely, to give an action of C star on affine varieties is the same as to give a grading on its algebra of functions. What does being contracting means? Contracting means that this grading is positive. Property 1, equivalent to saying that the grading is positive. By definition, says that the 0-degree component is a scalar, and negative components are 0. So I get a positive grading on this algebra of functions. Are there any questions? Let me now list some consequences of having this contracting action. First, and this is the easiest, one can show that the intersection of S with the closure of the orbit O is just the point E. Why? By transversality, it's an isolated point, and then every other point in the intersection will need to be contracted to here. The unique intersection point. Second, you can ask which orbits are intersected by S. And here is the answer. Some G orbit, the prime inside of the algebra G, then the claim that the intersection S and O prime is non-empty is equivalent to the following. We take our O prime, we can dilate it by C star. Doesn't matter whether by the usual action or the modified action, because this is stable. And take the closure, and this closure must contain. Okay. And then finally, what one can prove is that if an orbit intersects S, then this intersection is transversal, but in kind of in a weaker sense. Namely, that for every X S intersected with O prime, the tangent space to X and G, tangent space to X O prime, plus, not direct, tangent space at X to S. Say the sum. This also exercises. Finally, let me mention the special case, which is older than this construction. This construction is due to Slodowy. Following special case is due to Kostant. Trying to suppose for a moment that O is principal. What does this mean? It means by definition is that the closure of O is just the entire variety of nilpotent elements, known as a nilpotent. For example, for SLN, it means that this is a single Jordan block. And then what Kostant proved is the following important characterization. So we can consider our Slodowy slice S equivalent to G. Then from G, I can consider the quotient morphism, the spectrum of the invariants. Then the composition is an isomorphism. Huge result, it can be used for various things. For example, it can be used to prove that this variety is normal by the Serre normality criterion. That's how Slodowy slices first appear. By the way, if I move too slow or I move too fast, you are welcome to tell me. Principle can be both. Is there any right here?
On this half, yeah.
All right. So this is what I had to say about Slodowy slices. Let me now talk about the Hamiltonian reduction construction. This construction starts with the following setup. Let's say that I have some subgroup, algebraic subgroup, n inside of G. And then I have some element psi in the dual of the D algebra of n, which is n invariant. And from this, I'm going to produce a certain Poisson algebra in the following map. So let's consider the restriction map mu from G dual and dual. Just take a linear function and restrict it to n. And that's what's known as a moment. It's obviously equivariant with respect to the action of n. And now I can consider the fiber of this psi. Psi is invariant, the map is equivariant. So on here, I have an action of the group. And what I want to do, I want to consider the following algebra. I'll take functions on the separability, and I take an invariance. A little bit alternative way to write it down will be the following. Let's consider the following ideal. I all elements let's say going to use a span S of G of elements of the form x of x, where x is an n. And of course, these functions mu minus 1 of psi is just a quotient to the symmetric algebra by its ideal way. And then notice that S of G is Poisson. There is a unique bracket which extends the Lie bracket on the Lie algebra G. And so with this, I can equip algebra upstairs with a Poisson bracket. It's another exercise. So what are elements in here look like? They look like cosets, A plus I and B plus I, which are required to be n invariant. So I claim that the following operation, which takes such two cosets and sends them to the bracket of A and B plus I, is well defined. Doesn't depend on the choice of these representatives, and is a Poisson bracket. On my algebra. That's a very classical construction called classical Hamiltonian reduction. These two classicals are dependent from each other. Other questions? So, what would I like to do? I want to identify the algebra of functions on the slice S with one of such algebras. And for this, I need to explain you how to pick R and how to pick this sign. Go. How to find sign with of S identified with CU minus 1 on the side. And the second side is Poisson, so I will get a Poisson bracket. And the kind of the construction is, I mean, let me put it this way. There are like a lot of subalgebras and semisimple algebras whom one can spend the entire mathematical life with. And this is not one of them. That's actually, this actually is a bit artificial. So I'll begin with the following definition. I have an integer I, and I will write G sub I for the I eigenspace of the element H in this algebra tree. Okay. Then give you one more exercise. I claim that the following operation, omega xy, equal to the Killing form of E and X bracket Y, is actually a symplectic form on the graded component minus 1. Let's see that this at least makes sense. So this has degree 2. Both X and Y have degree minus 1, so at least kind of the degrees cancel out. Not immediately 0. Now, once I have a symplectic form, I can choose a Lagrangian subspace. Denoted by L, side of this G minus 1. And I will define the subspace N inside of G as L plus the direct sum of all graded components in degree less or equal than minus 2. That's some construction. What does it give us? Another exercise is that M is nilpotent Losev algebra. Losev algebra consisting of nilpotent elements. And therefore, in particular, I can exponentiate it and get an algebraic sum. So that's my N. And then psi going to be by definition the pairing with an element not so difficult to see that it's actually a character, and therefore it's invariant. The character precisely because this L was Lagrangian. This element is an invariant. So at the very least, I can run the construction explained on this part of it. And then, again, not very difficult to see that S contained a mu minus 1. That's huge because the eigenvalues of H and the centralizer of F are all less or equal than 0. Now there is a fact which is a bit more subtle, because this generality established by BunG and Ginsburg, but a special case was established long ago by Kostant. -1. I take 1/2 of it.
No, but I mean here, like here. Section.
Each one. What?
Why s belong? Why s is?
So you kind of have the shift by E. Then what do you shift? You shift all the components of degree less or equal. So you take all components of degree less or equal than 0 and half of the space of degree 1. Because you need to pair. That's like, this behaves like the annihilator of fact. This secretly leaves, well, I mean, I was lazy at your expense. If I weren't lazy, I would say that this lives inside of G star or G. I shouldn't say lazy. I should say something like I give the participants an opportunity to practice the material or something like that. It's the same thing, but sounds nicer. Again, if you want to do this inside of G, then this guy is E plus n power. Right? Now, there is the following fact due to BunG and Ginsburg. I can consider the action map from n times s, mu minus 1 of psi. This map is an isomorph. One a little comment, maybe an exercise, which allows us to see that the choice of n wasn't that bad, that the dimension of these two things coincide. Dimension of this n is 1/2 of the dimension of O. This kind of shows that it's not a ridiculous change. Okay. So a conclusion is that this fact does give us an identification between the functions on S and this Hamiltonian reduction. And therefore, we get a bracket. On the left-hand side. Remember, the left-hand side was also graded. We would like to understand how this bracket interacts with the grading. So here is how. Same is that as the degree of the bracket back to the grading is equal to -2. How do we see this? And also it's an important ingredient in proving this isomorphism. We would like to equip this one with a grading, independently of this isomorphism. That's how we do it. Now consider a modified grading on S of G. Namely, we require that the degree of the subspace G sub I is equal to I plus 2. in particular, G minus 2 lives in degree 0. And with this choice, that ideal I used here is homogeneous. Because the only kind of non-homogeneous part, a prior non-homogeneous part, comes when this pairing is non-zero. Psi has degree 2, pairing is non-zero and degree minus 2. Now declared to have degree 0. Then, of course, the Hamiltonian reduction requires grading. And you can equip everything here in this isomorphism with a grading, which my lazy choices make more complicated. Sorry? And see that the isomorphism here is graded. And then because of this 2 here, the degree of the Poisson bracket with respect to this new grading is minus 2. So what I do, I double the usual grading, that's the choice of 2 here, and then I shift it by inner grading, which won't change the degree of the Poisson bracket. All of the brackets on the Hamiltonian reduction. Let's try to do this. Is minus 2. Other questions? To finish this part of the discussion, let me again explain the special case which Kostant considered. I'm always principal. In this case, the subalgebra N is actually not so bad. Actually, very good. So I need a special choice of E and H. And choose E to be just the sum of simple root vectors. And H is going to be the element to row check. Row check is half the sum of all positive poles. Then, because of 2 here, actually the grading is even, there are no odd components. And our N is opposite maximal nilpotent subalgebra. Psi is what is called non-degenerate current. Okay, so I already raised this, but we had an isomorphism between C of S and the algebra of invariance. So this is a Poisson algebra. This is the Poisson subalgebra, but with 0 bracket. The Poisson bracket comes from the Lie bracket, and these guys are killed by Lie brackets with every element of G. So the bracket here is 0. And this is a Poisson isomorphism. Surprising. So the bracket here constructed equal to 0. Nothing interesting happens. All right. Maybe let me explain the construction of a quantization, and then we make a short break. Once you have something defined, a Hamiltonian reduction, then your best hope for quantization is just to quantize all ingredients of the Hamiltonian reduction and hope that it will do a job. But before I get there, I need to explain what I mean by quantization in this context, where I have a graded Poisson algebra. I'm going to consider a field at quantization. Want a field of quantization going to denote by QDW of this graded Poisson algebra C of S, by which I mean the following. W here is associative algebra. With the filtration, algebra filtration. W is the union of I bigger equals than 0, W less or equals than I. The degree of the Poisson bracket is -2, and correspondingly to this, I want the filtration to satisfy the following property. I take the Lie bracket of the part less or equals than I and the part less or equals than J. I want this to land in W less or equals than I plus J minus 2. And what this gives me is that if I take the associated graded with respect to my filtration, it's a commutative algebra, but also it has a Poisson bracket of degree -2, and this is a top degree in the commutator. Poisson is degree of the bracket equal to -2. And then the connection between this W and the initial algebra C of S is that I want a graded Poisson isomorphism between group of W and C of S. In other words, what I'm doing, I'm deforming commutative product C of S. Filter deformation meaning that I'm only allowed to put lower degree terms, and I want this deformation to be consistent with the existing Poisson bracket on C of S. That's what I want to construct. And now, how am I going to construct this? Let's recall C of S is a what? It's a quotient of S of G by the ideal I, and then I take invariance for the action of N. And then the size of span of S of G, X minus psi of X, where X is in the subalgebra N. So S of G, I know how to quantize. I need to take the universal enveloping algebra. S of G replaced with U of G. ideal I will be replaced with the ideal that I call J, and that's the direct analog of I, but inside of the universal envelope. Span G, that's the left ideal, x minus psi of x, where x is an n. And then I can still consider the action of the group on the quotient. And the claim is the W, which is the quotient of G by J. Invariance carries well-defined associative product, again defined by the most naive formula. I take one coset A plus J, even in here, another coset B plus J. Surprise, surprise, I define this to be a B plus J. And this is a well-defined product. Just a remark, before you take invariance, there is no algebra structure. No, not well-defined. It's only well-defined because these guys are invariant with respect to n. Questions?
So in the principal case, you can write this thing as endomorphisms of something, right? Of some inducers.
Yep.
Is that the case in general, or?
Yep. Exercise for people who like representation theory and characteristic zero fields is that W is identified with endomorphisms for U of G, U of G over J, and then opposite. If I were to play this data trick in characteristic P, I would get a bigger algebra. Characteristic P, invariance with respect to the algebra and invariance with respect to the group are different things. Characteristic zero, this is okay. And so the modern observation is that this guy becomes a bimodal.
It's like left versus right idea.
They're all identified in some way, but intermediate. Further questions? Now, I need two things. I need a filtration here, and I need an isomorphism like on top. Okay, so where do I get a filtration? Well, I have a modified gradient on S of G. For the same price, I can consider the modified filtration on U of G. Gives you a filtration on W. Well, you first get a filtration on this quotient, then filtration on its sub. But notice that the associated gradient of filtration here just gives you the commutative counterpart. J is identified with Fg mod I However, in principle, when you take invariants, the associated gradient can become smaller. So the only thing that we get from this isomorphism is that the associated gradient W canonically embeds into C of X. It's because taking invariants for an arbitrary algebraic group is only left exact, but not exact. However, and I already raised that fact, this inclusion is an isomorphism because the premise of the action of S on U minus 1 of S. So what's going on here, roughly speaking, is the following. I want to show that this is an isomorphism. I need some condition like x1 of n inside of here vanishes. I use it x1 with coefficients in a regular module is 0. That's roughly speaking how it is. So I constructed my quantization, and maybe before doing a 5-minute break and going for half an hour more. So do people want a break now? I just talk about the principal case for a couple of minutes. Okay, good. Case. For this principle. Now notice that in general, without this assumption, I have a homomorphism from the center, the universal enveloping algebra, which is a G invariant, into my double. Why? Because this U of G naturally maps, U of G invariance naturally maps into this quotient, then the image consists of n invariants. And what I get here is an algebra isomorphism, algebra homomorphism. It's fielded, where on the left-hand side I consider this doubled filtration, and it doesn't matter whether I shift it or not. And the associated gradient, this homomorphism is a similarly defined homomorphism from the invariance in C of G, C of S. Now, when O is principal, then this guy here is an isomorphism. For the initial guy is also an isomorphism. Yet the center of U of G is isomorphic to W. It's beautiful. All right, let's have a 5-minute break. 2:57. Hey, you want to give a lecture instead of me?
Started 1 minute earlier.
Right. So this construction that I have explained, it goes back to work of Priamet, who originally defines W-algebras. And then this combinatorial reduction interpretation is due to GAN and Ginsburg. It's kind of all nice. However, this subalgebra N is a bit unnatural. I want to give a construction which is more natural from some respect, but is less natural from some other respect. That's construction via quantum slices. And as before, I will start with a commutative situation. So what I want to do, I want to consider the maximal ideal M inside of functions of B. This is the maximal ideal of the nilpotent element B. Then I can form the completion of C of G at this element as the inverse limit of the quotients of C of G by the powers of this maximal ideal. And that's an algebra of formal power series. And then I can consider similarly completions of the functions on, let's say, O bar at E. So E is a smooth point here. I just look at the formal power series on the tangent space. And I can consider the completion of functions on S. Then the condition that TE of G is TE of O plus T of S can be rewritten as saying that I have an isomorphism of the completion of G at E with the complete tensor product of the other two completions. So this hat is a complete tensor. Meaning that I have two topological algebras. I tensor them, this has topology, but it's not complete. I complete it. Okay. And I have a isomorphism, let me give it a number, let me call it 2. And there are a lot of choices for this isomorphism. I want it, of course, to be compatible with this decomposition, but then kind of there are really a lot of choices. Very long. Now notice that this algebra here, and also this algebra here, are both Poisson. Poisson bracket tends to any completion, and then T of E is a symplectic vector space. This Kirillov constant, symplectic form. And so here is what I want to do. Proposition is that there is a degree -2 Poisson bracket C of S is the following property, such that this isomorphism 2 can be chosen Poisson and C times the cube. There are a lot of choices, but I claim that with a suitable Poisson bracket on C of S, that will then give me Poisson bracket here, I can make this isomorphism Poisson and C star equivalent. Where here I have that modified this direction from before, here I have its restriction, here I have some action. This action kind of again comes with a twist of the natural scaling action. Okay. This is a proposition. I want to give a sketch of proof, and that's the only thing I'm going to sketch of proof. So this construction is essentially in 2 steps. A proof I use some notation. Omega is a symplectic form on the dual of the tangent space. Going to denote by V. And then on this V, I have a Swiss action. So how does it exactly come to be? Well, I have an action on G which fixes E. And it restricts to an action on the tangent space, and I take a suitably dualized action on the Q. And so my first step is I want to produce, construct a C times equivariant map iota going from the space V to the completion of functions on G such that it's compatible with the Poisson brackets. Namely, we call this condition star. I take the Poisson bracket of iota of U and iota of V is equal to omega UV for all U and U, all inside of U capital. That's what I want to do. What does this have to do with the statement of the proposition? Well, if I have, as I say, the morphism 2 as I want, then this embedding will come for free. Embedding into the first factor. First factor, the Poisson bracket is defined exactly by this formula. I'm going to produce this embedding first. And how am I going to produce it? So I'm going to notice that this decomposition of tangent spaces just hands me a map iota 2 from V into C of G completed with E. I don't even need to take completion here, which is C star equivariant. Because this decomposition can be made C star equivariant. And such that this property star holds modulo m squared. Essentially use that the cotangent space is quotient of the maximal ideal modulo its square. Then kind of you get definitions for some time and you get. And then I start to lift it order by order. And then we find the star equivariant lift. Let's call it iota 3 of iota 2. Means that iota is equal to iota 3 modulo m squared. Such that star now holds for iota 3 at m cube, etc. And so here, so the first time you see this kind of argument, when you try to prove formal version of Darboux theorem. So there is an analytic proof of Darboux theorem which shows some conversion, but there is a even simpler formal proof. You lift your Darboux basis order by order. That's essentially what happens here. And then we take iota to be the inverse limit of iota j's. As j goes to b and does the job. Questions? So Now let's again get some inspiration from what we want to prove. In that, if the isomorphism on top is Poisson, then the second factor is the centralizer of the first factor, Poisson centralizer. So what I should do with my construction, I should now consider the Poisson centralizer of the image of iota. And one can prove that it's identified star equivalently with the completion functions on S. And at this point, this algebra here acquires degree minus 2 Poisson bracket. Like here is a Poisson subalgebra. That's Poisson bracket, degree minus 2. And I want to consider a subalgebra inside of this guy. So this is the algebra of formal power series. I want to consider the subalgebra of all locally finite elements. Right, C times finite, which is the following: is all elements in my original algebra that lie in finite dimensional C times subret. That's a subalgebra. And since my Poisson bracket has degree minus 2, I bracket 2 elements inside of here, I get an element inside of here. Poisson subalgebra. That's in fact what we need. Turns out that C of S, which a priori sits inside of the subalgebra, is actually equal to it. And this is because the grading is positive. Now think about the following situation. How can we recover polynomials in one variable inside of the algebra of formal power series in one variable? Formal power series, we have a cis direction. And polynomials are exactly the elements which lie in a finite dimensional subrepresentation, meaning only hit finitely many degrees. That's essentially what happens here. Let's finish the sketch. So 2 remarks. So this construction crucially uses iota, this embedding, and this embedding is very far from being unique. However, any 2 choices of iota are conjugate via Hamiltonian at moment. And you can choose it to be degree preserving. In particular, the Poisson bracket is well defined up to metamorphism. And second, the resulting bracket on C of S is isomorphic. Bracket from section 2.1, one which was obtained by Hamiltonian reduction. But this is not exactly obvious. We need to do some work in order to see this. Okay. Questions?
the motivation for taking the formal neighborhood around E?
You want a formal slice somehow. And why do you want a formal slice in this compatibility in Poisson brackets? That's because if you want a Darboux theorem in algebraic setup, you basically are doomed to use like formal neighborhoods. And this is some kind of a Darboux theorem. So now, the last part of the I want to explain the quantization of this construction. And so again, you look at the construction of the Poisson bracket and you just try to replace all the ingredients on the level of quantizations. So what I'm going to do, I'm going to take my universal enveloping algebra U of G. I'm going to equip it with doubled PBW filtration. The degree of G is equal to 2. And then I'm going to consider the result known by U sub H bar of G. I can explicitly describe it as a quotient of tensor algebra of G adjoining H bar by the relation x tensor y minus y tensor x plus H bar x1. Maybe H bar squared y. And now this guy is great. The degree of H bar is equal to 1. What does this buy me? Notice that we have an epimorphism, let's call it pi, from U H bar G, quotient by H bar. Nothing else is a symmetric function. Or I can say it's an algebra of polynomial functions only. Inside of which I have a maximal ideal, which I call M. I have my M complete. I'm going to consider its pre-image until the side of this completion. That's a maximal ideal. Quotient by this ideal is still the scalars. Now I'm going to take the completion. I have a two-sided ideal. While it lives in a non-commutative algebra, I can use the same formula for completion as before. I define UH bar G completed at E to be the inverse limit the quotients of UH bar G would be until the power M. That's a legitimate algebra. Whose quotient by H bar is just the commutative completion I considered before. Here is a fact that is not totally obvious. And the fact is that H bar is not a zero divisor in this completed algebra. And the hint is that even in this non-commutative setup, completion is still an exact function. It's kind of the same technique. Prove this as what you did in the commutative. Now, this completed algebra becomes a quantization, this formal quantization of the previous completed. So this guy here looks like a formal power series in dimension of g plus 1 variables. Now the product is non-commutative, it's default. I'm going to play with the same game as before.
Power series in H bar as well, or does that not matter?
Yeah. You need to add H bar, otherwise the magic is not going to work. Oops. That. So what do I do next? Well, I essentially repeat the construction that I did at the classical level. Let me just do it by steps. So first I construct iota tilde going from V to H bar. We completed the theme such that the bracket of iota tilde U, iota tilde V is H bar squared omega UV. If I divide, this is divisible by H bar squared, bracket of all elements are. Let's leave the Poisson bracket. Do this in the same way as before. Then I take W prime H bar to be the centralizer of the image of this map. This is a subalgebra. It's acted on by C star because I can assume that my iota tilde is C star equivalent. I pass to C star finite elements. I can denote this by W sub H bar. So W prime quantizes the sense of deformation quantizations. C of S completed E WH bar quantizes those above polynomials, young because all the degrees are positive. And finally, I set W to be WH bar modulus the ideal H bar minus 1. So this guy is graded. This is going to be a field attack. Questions? Algebra, in fact, is amorphic to quantum Hamiltonian reduction. But this is also non-trivial. Okay, so what have we done? So 90 minutes of time. We have produced one Poisson algebra in two different ways, and we have produced its field quantization in two different. Now you can ask what's next somehow. What do we do with all this? First, one could study representation theory of this W algebra and its interactions with the representations of the universal enveloping algebra. Namely, one can study functors between category of modules over U of G. Modules are maybe bimodules. And modules over or bimodules over W. And let me just give you one example of such a functor. So I can consider the so-called generalized Whittaker module. Going to denote by WH sub E, and so all modules over U of G such that elements of the form x minus psi of x act locally nilpotently for all x in that subalgebra n that I produced in the first part. And this category is equivalent, in fact, to the category of all modules over the W algebra via the bimodule. And somehow this is more useful in the principal case because the subalgebra is nice, but in the general case, the subalgebra is God knows what. So this is not so useful. There are other functors. And somehow a common feature of all these functors is that they are more convenient to study using the slice constant. Most notably, there are functors between categories of Harish-Chandra bimodules. There are functors between categories O, functors between Harish-Chandra modules to some. There's a lot more, and kind of this all uses quantum sizes. So that's one remark. Another remark is that there is an affine story. That this seminar is about. So the traditional definition of affine W algebra is traditional general definition. Yeah. Some kind of quantum Hamiltonian reduction. It's more complicated because it's a semi-infinite one. In the principal case, you can do something related but different. You can use so-called screening operators. Well, Danya has pleasant memory of what happened in the spring. Screening operators, like like any kind, like when you are screening an airport, it's not pleasant, right? So screening operators are not pleasant. but they give you some benefits, in particular the Canadian triangle duality. From what I understand, is also a topic in the seminar. Then kind of I'm 19% sure there is a quantum slide constant. One needs to kind of have some fun with H-parodic vertex algebras, other things. And in principle, I kind of expect that hopefully we'll clarify some things about affine W-algebras and superalgebras. That's where I want to stop.
Any questions for the speaker?
Kind of non-principal, on case do you expect this to have some interpretation? What do you like? Or
I don't know. This hasn't been done yet.
Out of time, we should up here. All right, 1 minute. All right, let's thank our speaker again.